Let's take a look at example number 6. So for each angle, we're supposed to find the angle of least positive measure. So what that means, it is the smallest possible positive angle that is coterminal to the given angle. So for part A, we have 908 degrees. And I think the best way is to first draw a diagram to see what operation we can carry out that might lead us to the answer. Let's attempt to draw 908 degrees. Okay. So vertex at the origin, initial side along positive x-axis. Now 908, well, that's definitely going to be more than one cycle, right? Because one cycle is 360. In fact, it's going to be more than 2 cycles because 360 times 2, meaning 2 cycles, is 720, and 908 is larger than 720. Let's see if it's larger than 3 cycles. 360 times 3, well, not larger than 3 cycles, right? 3 cycles is 1080, so that means it's right above 2 cycles. To see how many additional degrees we would need to complete, we can take 920 and subtract away the 2 cycles, so 2 times 360. And sorry, I think I should have written 720, right? Sorry, 908, that's what's given to us. 908 minus 2 times 360, excuse me. So 908 from this quantity that's given to us. And we're subtracting away the 2 full cycles to see how many additional degrees it's rotating. So it's rotating 108 additional degrees. Okay, so what that means is that, and I'll leave this up here if you'd like to see that. What that means is we're completing 1, that gives us 360. We're completing 2, that gives us 720. And then in order to make it to 908, we're still 188 short. So we're going to have to rotate another 180, and then 8 would be just an additional little piece there. So we're going to end up with the terminal side in quadrant number 3 that more or less finishes there. Okay, so let's write some work about how we got that diagram. I'm basically going to just write down what we did on the calculator. On the calculator, what we did was say something like 908 is going to be the result of taking 2 whole cycles, so 2 times 360, plus some leftover, and that leftover is 188. The reason being is that 2 times 360 gives us 720, so then 720 plus 188 gives us the 908. Okay. Now, they want a coterminal angle, meaning it has to have the same initial side, same terminal side, but a different angle measure. So, and not only that, but the angle measure has to be as small as possible as long as it is positive. Any ideas as to how we might be able to accomplish that, or what might be the answer? Okay, well, let's see. If I want to come up with a positive angle, that means that I have to rotate counterclockwise, right? So here's my initial side. I'm going to rotate until I make it to my terminal side. And I don't want to complete a cycle and then make it to the terminal side, because that's going to already give me an angle that is larger than what we've found here, which is just this little piece from the initial side to the terminal side without completing any cycles. What is the measure of that orange angle?
188.
188, very good. Yep, it's 188, because remember, that was the leftover degrees besides the 2 full cycles that we had to complete in order to make it to the terminal side. So that means that 188 is the coterminal angle with the least positive measure. And so let me just write that down. 188 is the smallest positive angle that is coterminal to 908. We're not going to be able to find any angle smaller than that that is coterminal to 908. Is that okay? Any questions there? Now let's try part B. For part B, we have negative 75 degrees. So I'm going to start by drawing a diagram. Now, negative 75 degrees means we were opening clockwise away from our terminal side. So that means we're going to open down, and then we won't make it past the negative y-axis, because at the negative y-axis, this is already negative 90 degrees, right? So we're going to be 15 degrees short of negative 90 degrees. So I'll say it's about there. That's our negative 75. And we want to find, again, the angle with the smallest coterminal angle with positive measure. So that means that I'm going to open counterclockwise away from the initial side until I reach the terminal side. So that would be the angle that I've just drawn here. How might we be able to find that angle measure? Well, let's see if, go ahead, sorry.
Would you just do 360 minus 75?
Yeah, very good. Yep. So we'll just take the 360, subtract away 75 degrees, right? So it's almost as if we would have tried to complete 360, but we were stopped by this negative 75. So we subtract that away. And that is going to give us a 285? 285? Let's see. Yeah, 285. So it's opening counterclockwise, that would be positive as required by the directions. So 285 is the smallest positive angle that is coterminal to negative 75 degrees. All right, so any questions there? Is it okay if I turn this page over?
Yeah.
Yep. Nope. Yeah. All right, so we're going to continue on to page 9. And actually, my 9 is on a different page, so I don't have to turn that one over. I can leave it on. Okay, so for page number 9, we're looking at some application problems, applications of radian measure. And if you recall, radians was one of the units of measurement for angles, the other one being degrees. And so for these application problems, we're going to be taking a look at two formulas. One of them is for arc length, and the other one is for area of a sector. So before we take a look at the formula, let me just briefly explain what is arc length. Arc length is the distance along the circumference of a circle. So like in this case here, the S is describing that length. It's the same as if I were to take a piece of string. So let's say this string here, and I were to try to find or I would align the piece of string with the circumference of that arc. Then the distance, once I straighten that string, the distance from the tip up to where I've finished measuring that distance would be the arc length. So that's S, arc length. And according to this formula, it's telling us that the arc length is equal to the radius. So the radius of the circle being this here, which I'll color code red. So it's the radius multiplied times the measure of the angle theta. So multiplied times this angle here. Now what we have to keep in mind about that angle is that it has to be given in radians. So please underline that or highlight it, because that's actually very important, and it's a source of common mistakes that sometimes people will try to compute arc length using degrees instead of radians, and they get an answer that is incorrect. So please make sure that you highlight that or box it as a reminder that it should always be in radians. Now the next formula is the formula for the area of a sector. And so when it's talking about area of a sector, it's talking about the area in this piece that I'm highlighting here. Okay. And the formula for that is 1/2 times the radius squared times the measure of the angle, where the angle again has to be in radians. Okay. So let's attempt example number 7. Example number 7 reads, a center pivot irrigation system provides water to a sector-shaped field with a radius of 321 meters and the central angle of 15 degrees. Find the area of the field. Okay. So let's draw a diagram, because that's always a good idea. It helps us picture what's going on. We can then determine what formula we need to use and what are the quantities that are being given. Okay, so think of it kind of like if you've been to a baseball, field, or any kind of, larger playing field. The irrigation system, there's some pivot that shoots out water, and then it rotates some amount of degrees. So that's the situation that's happening here. In this case, the pivot shoots out water 321 meters out. So it's a pretty strong pressure that it must have. And then it's rotating around a central angle of 15 degrees. So it rotates 15 degrees. And shoots out water same distance, 321 meters. So we can expect this sector to be formed. They want us to find out what is the area of that piece of field. So radius, we know it's 321. Angle, we also know is 15 degrees. But if you recall from the formula, the angle has to be given in radians. So we're going to have to manipulate that a little bit before we're able to apply it with the formula. So in order to change, do you guys remember what we're supposed to do if we're trying to change from degrees to radians?
Was it 360 over 1 or 1 over 360?
So it's similar. It's something close to that, but let's see. I'll write it this way. So 180 degrees, we know that's the same thing as pi radians, right? 180 degrees and pi radians are the same thing. They measure the same angle. So if we want to get rid of the degrees and be left with radians, what ratio did we have to multiply by? What should go in the denominator?
180.
180, good. And then in the numerator, what should we have?
Okay.
1.
Well, the pi. Yeah, the pi. And so we will always want to make sure that this is dividing out to a 1 in relation to what it's measuring. In this case, since both of these units of measurement measure an angle that has that same half cycle, okay, measurement, then you could say that these two kind of equate to the same value, so they divide out to 1. So we're not changing the value of 15, we're just simply changing it to radians. Okay, so working through this is going to become 15 degrees over 1 multiplied with pi over 180, and that's in degrees. Now, because we have degrees in the numerator and denominator, those are going to cancel out. We can just multiply across to get a 15 pi over 180. And then we can try and simplify it a little bit. Ultimately, it's not going to matter too much because we're going to punch it into our calculator when we plug it into the formula. But just because we don't like to leave fractions that haven't been simplified, let's see if 180 is divisible by 15, because then we can reduce. Yep, it is divisible by 15. So what we'll do is we'll divide the top and bottom by 15. Right, and that's going to leave us with pi over 12. Okay, so what is that pi over 12? That is the measure of the angle in radians. And now we can apply our formula. The formula reads the area is 1/2 radius squared times theta. That would be a 1/2 times 321 meters, and that's going to be squared times a pi over 12 that we got for the angle theta. We can punch it into our calculator, and we're going to get, let's see, 1/2 multiplied with 321 squared multiplied with a pi over 12. And that's going to be, we'll round to the nearest meter squared. So that's going to be 13,488 and meters squared. Now, why is it meters squared? Well, because the radius is measured in meters and we're squaring the radius. So you can think of this m as also receiving the square, and that's read as meters squared. All right, so questions there for our final answer? All right, let's take a look at example number 8. The latitude of city E is 42 degrees north, and that of city D is 34 degrees north. If the radius of the Earth is 6,400 kilometers, find the north-south distance between the two cities. Okay, so then I'm going to draw a diagram to get a better picture. I'll draw half of the Earth because we're really only interested in the half of the Earth that the two cities are on. So I'll draw the north and south pole. Okay, here's north, here's south, and here's half of Earth. And that horizontal line that I've drawn would be like the equator. Okay. So at the equator, that is just the 0 mark. Okay, then if we move above the equator, that's where we start counting degrees in the north direction. If we move below, then they're considered to be degrees in the south direction. Now in this case, they're giving us one of the cities, city E, to be in a direction 42 degrees north. So 42 degrees, I'm just going to approximate it, is about there. Okay. That would be 42 degrees. And then the second city, city D, is 34 degrees north. So let's see, that's a little bit lower. I'll use a different color pen. So that there measures 34 degrees. They tell us the radius of the Earth, approximately, it's 6,400 kilometers. So what that means is that from the center out into the edge, or right at the crest, then that would be about 6,400 kilometers. And now they want us to find the north-south distance between the two cities. So the north-south distance would be this distance up here, right? The distance that someone could actually travel. So if you own maybe a car, you would want to travel, through the surface of the Earth and make it to city D. So let's see if we can first figure out which of the two formulas we want to use here. If we're talking about a distance, which formula is the one that applies distance?
Arc length.
Arc length, exactly, good. So we're looking at S is equal to R times theta, where S is this arc length here. Now, in order to use the formula, we need to know the radius, which we have. They gave to us as 6,400 kilometers, so that's good. We also need to know the angle that the measure of the angle that is part of the arc length, that is part of this little piece. So what we're looking at then is the angle here, which is unknown, right? We don't know, they didn't give us the measure of that angle. And now there's quite a bit going on, so I'm just gonna redraw that same diagram, but maybe without this lower half of the Earth, since we don't really need it. I'm just gonna focus on the location of the two cities in this north direction. Okay, so we have this larger angle measuring 42 degrees, and actually let me draw that down here. We have the smaller angle measuring 34 degrees. And we're attempting to find the distance between these 2 points, because that is where E and D are at. And so we're saying we need to know what is the measure of this angle theta. Okay, so any ideas as to how we might be able to find that angle theta?
Minus 42 from 34.
Good, yeah, so 34 minus 42, good. So theta is going to be 42 degrees minus 34. And if you're a little confused as to why, well, just think about it this way. 34 degrees is this angle here by itself. Theta is this green angle. Together, they add up to 42 degrees, right? 34 degrees plus theta make up the 42 degrees. So if we want to find out what theta is, we simply solve for it by subtracting a 34 from both sides, and that's how we end up with theta is 42 minus 34. Yeah. So that is going to give us 8 degrees for theta. Now, same as with the formula for area, arc length requires the angle to be in radians. So we're going to have to convert that to radians by the same operation as what we had last time. That is, multiply by a pi over 180 degrees. And so then what comes of that is 8 degrees over 1 times 8 pi over 180. The degrees are going to cancel out, and we're going to end up with 8 pi over 180. You can simplify this. In fact, if you divide top and bottom by 4, which is, by the way, the largest common factor that they have, it would just give us a 2 pi over, what is it, 45. 180 divided by 4 is 45. Okay, so I'm dividing top and bottom by 4 to reduce it down to 2 pi over 45. So now we're ready to find the arc length. The arc length is going to be the radius, 6,400 kilometers, multiplied with the angle in radians, that's a 2 pi over 45. Now we can punch it into the calculator. So 6,400 times 2 pi over 45. That gives us approximately, I'll round to the nearest kilometers, so approximately 894 kilometers. Well, for the first time, we're actually going to address the trigonometric functions, right? Up to now, we've just been seeing terms and definitions that are related to trigonometry, like angles and degrees, radians. But now we're actually going to talk about what the functions are. And so to talk about them, we want to consider an acute angle. And remember, acute means that it's less than 90 degrees. This is very similar to what we're seeing here on page 10 at the top of page 10. And we want to think about all of the sides that are related to that angle. And so, of course, the way it's drawn here, we really have only one or maybe two straight sides, right? The positive x-axis and the terminal side. And so to get a third side, we're going to draw a right triangle. That means that we're going to want to have a 90-degree angle. And the way to do that is to just draw this vertical line. And then I'll draw the symbol here for 90 degrees or right angle. Yeah. And now there's the three sides associated to this acute angle. We call this bottom side on the positive x-axis, we call that the adjacent side. And then the side that is directly in front of the angle, and so the one that's opening directly in front of the angle, this one we call the opposite side. And then in every right triangle, the longest side is called the hypotenuse. I'm just going to abbreviate this HYP. And I'll also color code those as well. I'll keep this terminal side red, the same color we've been using up to now. And then the adjacent side, I'll keep it green. This is our initial side. And I'll just introduce a new color here. I'll have the opposite side orange. And so the trig functions, they relate two sides together to the angle. Okay, so they take a ratio of two sides, and then that's defined to be a certain function of that angle. So let's just think about what are the different ratios that we can have between two sides. And I'll start us off. So I can think of like adjacent, and adjacent I can relate it to hypotenuse. So one ratio could be adjacent divided by hypotenuse. We could also have the reciprocal of that. We could also have hypotenuse divided by adjacent, right? Those are two different ratios that we can have. We could do the same thing for opposite, right? Opposite, I can relate it to hypotenuse. And so we would have opposite over hypotenuse. That's one ratio. Another one would be hypotenuse over opposite just by taking the reciprocal. Yeah. And then what's the remaining two ratios that we can form with these three sides, or with two of the three sides, I should say? Any ideas? So let's see, we have adjacent with hypotenuse, opposite with hypotenuse. We could also relate opposite with adjacent, right? We could form, for instance, opposite over adjacent, and the reciprocal of that, which is adjacent over opposite. Good. Yep. And so what we get then are 6 different ratios that we can form with these 3 sides. Okay. All of these ratios have a name. This first one, the second one, opposite over hypotenuse, that's actually sine, okay, which is this first one. I'm going to start writing those definitions here now. Okay, so sine of the angle theta is defined to be the ratio opposite over hypotenuse. Okay. Remember again, opposite is the side that is directly in front of the angle. Hypotenuse is the longest side of the triangle. And then the reciprocal of this, the hypotenuse over opposite, is called the cosecant of the angle theta. So this is hypotenuse over opposite. And I'll write here in full what the name is, because this is an abbreviation, CSC. It stands for cosecant. Again, this is now reciprocal hypotenuse over opposite. Okay. And then the full name of this, again, this is an abbreviation. This is abbreviation for sine. For cosine, this is defined to be adjacent over hypotenuse. So the adjacent side divided by the hypotenuse. And so the adjacent side we've color-coded green, hypotenuse is red, and this is cosine. Secant is defined to be the reciprocal of cosine, meaning it's hypotenuse over adjacent. And this is secant. And then finally, we have tangent and cotangent. Let me just go ahead and highlight these with colors. Tangent is defined to be opposite over adjacent. And the full name is tangent. Cotangent is the reciprocal, so it would be adjacent over opposite. All right, and again, I'm just going to go ahead and color code. Now there's a very useful kind of like, it's not really an acronym, it's just kind of like a way that's used to remember this. And it's SOHCAHTOA. Have you guys heard of that before? If you have taken trig before? SOHCAHTOA. So stands for sine, the S stands for sine, and it means opposite over hypotenuse. Okay. Then the C stands for cosine, and it is adjacent over hypotenuse. Excuse me. And then there is TOA. The T stands for tangent, and we get opposite over adjacent for it. Okay, so this is one way to remember it. SOHCAHTOA. For these first 3 trigonometric functions. The rest of them, I'll tell you guys how I remember them. Let me just finish highlighting this here. Okay. The rest of them, the way that I remember them is that the S and the C are always paired together. So like sine is always paired with cosine. The cosine is paired with secant. Okay, so those two are reciprocal of each other. And then there is tan and cotangent. Well, those just sound alike. Okay, so tangent and cotangent are the exception to that rule. Those are the reciprocals of each other. But for all the other one, you always have C paired with S. Okay, C paired with S. Okay. Any questions on the definition? And we're going to see some examples with that. In fact, what I'll do here is I'll put a pause on this portion of the lecture notes, the bottom of page 10. Let's pause on that for a moment so that we can see the trig functions with some actual numbers. Okay, so let's go to page 11 now on example number 9. Okay. Example 9 is asking us to find the 6 trig functions of angle A. Okay, so the angle that we're interested in is this one here. That means that relative to angle A, we need to find what are the opposite, the adjacent, and the hypotenuse. So the hypotenuse is always the easiest one to spot because it has to be the longest of the 3 sides. It's also going to be opposite the 90-degree angle. Okay, so this is our hypotenuse. Then the opposite side has to be directly in front of the angle. So which side is the opposite side for us? So yeah, so it's not well, let me be careful. It wouldn't be the little c, but it would be this side here, the BC. Yeah, the BC, good. So the BC is the side that is directly opposite or in front of the angle A. Okay, so that's our opposite side. And finally, the adjacent side is the one that gets that's left over. The way to remember the adjacent side too is that the adjacent side has to form part of the angle A. Okay, so like here it forms part of the angle A along with the hypotenuse. The opposite side will never form part of the angle. Okay, so that's another way to remember which one's which. All right, so now we're going to find the 6 trigonometric functions of angle A. We're going to start with sine of angle A. And remember, sine of angle A is so. Okay, so it's opposite over hypotenuse. And I won't always write the definition, but I just think it's good practice for now since we're being introduced to them for the first time. So the opposite side is going to be 36. The hypotenuse is going to be 85. And then we would want to check if this can reduce, but this is 85. That's just going to be, well, maybe it's easier to think about it in this form. The 36 is a 6 times a 6, which breaks down into a 2 times a 3. So we would have a 2 times 2 times 3 times 3. 85 is going to have a 5 as a factor. In fact, when we divide it, we get a 5 times 17, and both of those are already prime. So that means they don't share any common factors, right? Because this only has 2s and 3s. This one has a 5 and 17. Nothing shared in common, which means we can't reduce that. Okay, the next thing we're going to take a look at is cosine. And cosine, remember, it's ha, AH. So that's adjacent over hypotenuse. And the adjacent side is 77. The hypotenuse is 85. Next one is tangent. Tangent of A is opposite over adjacent. Okay. Opposite side is 36. Adjacent side is 77. Again, I'll leave it to you guys to verify that these don't share any common factors, so we can't reduce this fraction. And then come the reciprocals. Okay, so I'm going to take a look at what is the reciprocal of sine. Okay, so first, which trig function, excuse me, is a reciprocal of sine? Is it secant, cosecant, or cotangent? Cosecant, good, thank you, Christian. It's cosecant, remember, S with C. So it's cosecant of A. And if it's the reciprocal, that means that we have hypotenuse over opposite. Okay, so hypotenuse here is 85. Opposite is 36. And we have our cosecant. And let's now take a look at the reciprocal of cosine. And for cosine, is it going to be cotangent or is it going to be secant? Secant, good. It's going to be secant. And if it's the reciprocal, it means that we're going to take this and flip it. So we'll get hypotenuse over adjacent. And hypotenuse is 85. Adjacent is 77. All right, last one. We've got cotangent, and that's going to be the reciprocal of tan. Remember, those are the only two that sound like each other. And if it's reciprocal, we're going to have adjacent over opposite. Okay, so the adjacent side is 77. The opposite side is 36. Those would be the 6 trig functions of angle A. Any questions? Okay, so let's go back to page 10 then. At the bottom of the page, when we're looking at the relationship between sine, cosine, tangent, and cosecant, secant, cotangent. Again, I'll just write like sine theta, cosine theta, and tangent theta. Now, if they are the reciprocals of each other, so if sine is a reciprocal with cosecant, that actually means that it's 1 over cosecant theta. Okay. And we can show that that's the case. We can prove it because, okay, so here's like our proof. If we start off with sine of theta, we get sine of theta, the definition is opposite over hypotenuse. And if we want to relate it to cosecant, we get cosecant is hypotenuse over opposite. So that's the same thing as 1 over hypotenuse over opposite for this here. Remember, whenever you divide by a fraction, it really means multiply by reciprocal. And that's 1 over cosecant theta. So that's a special relationship. If the proof seems a little iffy, don't worry too much about it right now. I'm not going to test you guys on proving this aspect. Later on, we'll get much later, maybe like I think it's week 10. We're going to get into proofs that look like this. So for now, it seems a little weird, but don't worry too much about it. What matters is that sine and cosecant share this relationship, that because they are reciprocals of each other, if I have sine, that's the same as 1 over cosecant. Okay. And then for cosine, it's 1 over its reciprocal, so 1 over secant. And for tangent, it's 1 over cotangent. All right. Okay, so let's come back to page 11. And we're gonna try to remember some special right triangles that we might have seen earlier in some other math courses. And that is the special triangles 30, 60, 90 and 45, 45, 90. Okay, for a 30, 60, 90, it has a special relationship between the sides. If the shorter side is x, then the hypotenuse is always twice the shorter side. And then this longer leg is going to be the shorter side times a radical 3. And that's true about all 30, 60, 90 triangles. So for instance, let's say that this x were a 5. Okay, so this bottom short side is 5. That means that this one here would be a 2 times a 5, which is a 10. Okay, the hypotenuse would be a 10. And then this longer leg would be 5 times the square root of 3, which would just be 5 radical 3. So that's how that one works. And then the 45, 45, 90, the 2 legs have to measure the same. And then the hypotenuse measures whatever this length is times radical 2. Okay, so again, let's say that this measures 9. And this other leg also has to measure 9. And the hypotenuse has to measure 9 radical 2. Those were some special triangles. And we're going to be using, the reason why we're going over them is because sometimes we're going to encounter problems in which not all of the sides are given, and they're going to ask us to find the 6 trig functions. Okay. Well, to find the 6 trig functions, we need to know the lengths of the sides. So we're going to have to rely on our knowledge of the 45, 45, 90, and 30, 60, 90 to come up with the rest of the sides. Okay. That's, of course, only in the case where you are given one of these 2 types of triangles. So for example 10, we have that, right? We have 45 degrees, we have 90. What does that force angle B to be? And what type of triangle do we have?
45.
Yeah, it has to be 45. The reason being is that the sum of the angles in a triangle have to add up to 180, right? So you can always, if you are not too sure, you want to justify it for yourself, you can say, well, 180 is supposed to be the sum of the angles, so we've got 45 degrees for A plus 90 degrees for C plus an unknown angle B, and then just solve for B and you'll get that it's 45, right? So this would be like 135 plus B is equal to 180, and then 180 minus 35, you'd get B is 45. Okay, so now that we know it's 45, we can apply this. You can think of it kind of like a formula for the 45, 45, 90. This bottom side is 5. What does that mean for this leg here? What's the length for that for BC? 5 as well. Good, because that's another leg, right? So 45, 45, 90, the legs have to measure the same. So in this case, this 5 means this has to also measure a 5. Okay, what about the hypotenuse? What does the hypotenuse measure?
5 radical 2.
Yeah, very good. Thank you. 5 radical 2. So this here is going to be 5 square root of 2. Okay, good. So now we have all the sides, and now we can find the trig functions of angle A. So again, this bottom angle is the one that we're interested in, and we can easily identify hypotenuse. Hypotenuse is the wrong side, which is this one. Then we can find what is the opposite side by looking directly in front of the angle. So that would be this side here. And the adjacent side is the one that gets left over, which also forms part of the angle. Okay. This is opposite, this is adjacent, and this is hypotenuse. So let's take a look. Sine of angle A is going to be what? Or even just in terms of the definition of it, what is it? Good, opposite over hypotenuse, good. So, oh my gosh, I'm sorry, I wrote these the other way around. And this should be opposite, right? All right, for this one should all be opposite, and this one is adjacent. The colors are right, but I don't know why I flipped the symbols. Okay, but this is opposite hypotenuse, so we're going to get 5 over 5 square root of 2. And if you want to write the definition again, I think that's great practice. That way you remember the definitions of these. Okay, so we get 5 over 5 radical 2. Now in this case, the 5's cancel out, so we get a 1 over radical 2. And then we don't like to have radicals in the denominator, so we want to make sure that we rationalize by multiplying top and bottom by the square root of 2. And so what that's going to give us is a square root of 2 over 2. Okay, that's for sine of A. Good. What about cosine A? What's the definition of cosine? Adjacent over hypotenuse. Good. Adjacent over hypotenuse. So now adjacent side is 5. Because it's the same as the other one, because there's a 45, 45, 90. And my hypotenuse is 5 radical 2. So exactly the same thing is going to happen, right? The 5s are going to cancel out. We're going to end up with a 1 over radical 2. But then we're going to want to rationalize that. So the final outcome would be a square root of 2 over 2. Right. And we have tangent. What is tangent? Well, that one is going to be, remember TOA, it's going to be opposite over adjacent. So opposite is 5, adjacent is 5. This is going to reduce down to just 1. All right, and so those are the first 3 trig functions. To find out the rest, excuse me, we can go ahead and just take the reciprocals of the first 3. We just have to remember what corresponds to what. So cosecant of A, that one corresponds to which trig function? Which of the first 3? To sine. Good, thank you. To sine. So that means that we would go up to sine and then take the reciprocal of it. It would give us a, okay, so this is where we want to be, we can save ourselves some work if we're clever about it. Because sine of A is the square root of 2 over 2. So if I take the reciprocal, I'm going to end up with a 2 over radical 2, which is going to require that I rationalize and do square root of 2 over 2, square root of 2 over square root of 2 to multiply top and bottom. And that's going to give us a 2 radical 2 over 2. That means that these are going to cancel, and we'll end up with a radical 2, right? So cosecant of A will be radical 2. But I want to show you guys how we could have done that or come across that answer a lot more quickly. Instead of taking this version of sine, we could have taken this original one that we got before we rationalized. Okay, so before we rationalized, we had gotten just a 1 over radical 2. So if I take the reciprocal of that, it's going to be a radical 2 over 1, okay, which is just radical 2. And that would save me this rationalizing step. So that's what I'm going to do. I'm going to take this 1 over radical 2, take the reciprocal, which is radical 2 over 1, and it simplifies to just radical 2. Questions there? Or at any other point? And what about for secant? What's the reciprocal of secant? Good, it's going to end up being the same answer because it's the reciprocal of cosine. In cosine, before we rationalized the answer that we got for it, it was a 1 over radical 2, right? So then if we take reciprocal, we're going to end up with a radical 2 over 1, which is going to be the same thing. All right, and we have one last one, and that is cotangent A. Cotangent A, we're going to take the reciprocal of tangent, which was a 1. So we'll have a 1 over 1, and that is just a 1. All right. Okay, good. Do you guys have any questions there?
Give me a minute. Where did you get that 2 over the radical 2 on the post-it note from?
Over here?
Yeah.
Yeah, so that one came from trying to find the reciprocal of sine. So sine, the final answer that we got was this one, the radical 2 over 2.
Right.
And so then I took reciprocal, which means the denominator becomes numerator, and the radical 2 comes to the bottom. So we get 2 over radical 2. This would be for cosecant of A.
Oh, I was mixed up. Never mind. I get it. Okay.
Yeah, okay.
That's to find cosecant. Okay. Never mind.
Yeah. You guys have any other questions? But this was a long way, right? This was a long way to find cosecant. And that's by using this answer. It's easier if you use the non-rationalized version of sine to find cosecant. Okay. So I want us to think about the same problem, the same triangle, but now I'm going to leave this as x. Okay, so let's say that we were to have a triangle. It's a 45, 45, 90. And that doesn't look exactly like 45, 45, 90. The bottom side's a little bit longer, but let's just pretend that they're the same. Okay, so we've got ABC, where this is the right angle. This is 45 degrees, and this is x. And they're asking us to find all the trig functions of angle A. Excuse me. Okay, then because it's a 45, 45, 90, we would know that this is x, and this is x radical 2. And we can start by finding sine of angle A. And the sine of angle A would be opposite over hypotenuse, which is going to be, remember, opposite side has to be directly in front of the angle, so this would be our opposite side. And then hypotenuse, well, that's just the longest side, so that's this one here. So opposite would be x, hypotenuse would be x radical 2. If we have the same number in the numerator as the denominator, they're going to cancel out. So we're going to end up with a 1 over radical 2, which would rationalize to a square root of 2 over 2. And that's exactly the same thing that we got when x was 5, right? Let's see if the same is true with the cosine. Well, with the cosine, we have adjacent over hypotenuse. And adjacent side is now this bottom side here. So adjacent would be x, hypotenuse would be x radical 2, which is exactly the same thing. And we're going to get 1 over radical 2, which will rationalize to a radical 2 over 2. Because the process is the same thing. And finally, let's take a look at tangent. I won't worry about the last three, because I think that at this point we can see what's going on here. We're going to see some pattern going on. Okay, but if we look at tangent, tangent is opposite over adjacent. And opposite side is x, adjacent side is x, and x over x is just 1, right? So what we're seeing here, what this is telling us is that the actual lengths in a 45, 45, 90 are irrelevant to what the sine, cosine, and tangent are going to be. And as a result, what secant, cosecant, and cotangent will be, because those are just the reciprocals, right? So it doesn't matter whether you have a 5 or a 500, sine of this angle, 45 degrees, is going to be the square root of 2 over 2. Cosine of 45 degrees is going to be square root of 2 over 2. And tangent of 45 degrees is going to be 1, always, regardless of the actual length. Okay. Which I think is pretty interesting. It's pretty... All right, and so I'm just going to go ahead and replace the A for what it is, which is 45 degrees. And I'll leave this sticky note on this page so that once I scan it, you guys have this as part of your notes as well, because that's kind of important. Any questions with that problem or this sticky note? All right, let's try example number 11. So example number 11 is asking us to find the 6 trigonometric functions of angle A. Okay, and here is angle A. Okay. We don't have all of the lengths yet, so let's first work on that, and then we'll identify what's the opposite, what's adjacent, what's hypotenuse. And so first, I have a 30, I have a 90-degree angle, which forces this to be a 60 degree, because remember, they have to add up to 180. So 30 plus 90, that's 120. 180 minus 120 will give us 60. So it has to be 60 degrees. Okay. And now that we know it's a 30, 60, 90, opposite to angle 30, we always have the smallest side, right? We always have x. And then what does that mean for the hypotenuse? In the formula, what is the hypotenuse usually? If we have x, that is. Go back to,
2x.
oh, sorry, go ahead. Yeah, 2x, right? 2x. Okay, so if the hypotenuse is 2x and 2x and the hypotenuse is 8, so that means that both of these are equal. What does that mean for x? What does x needs to be?
4.
4, good, yeah. Okay, because remember, this length has to be double this. So this is 8, this has to be 4. Good. And that actually helps us with this bottom side as well, because this bottom side, which is opposite to 60, is always going to be x radical 3. Right, so in this case, it's going to be 4 radical 3. All right. So that's the triangle aspect of it. Now let's look at the trigonometric aspect of it. We're interested in angle A, so we need to know the opposite side. And opposite side is going to be directly in front of the angle. So that's over here. Yeah, so that means that 4 is the length of our opposite side. Then we have the hypotenuse, which should be the longest side. Also, it's opposite to the 90-degree angle. So here's our hypotenuse. And finally, we have the adjacent side, which is this bottom side that forms part of the angle A. So that would make the 4 radical 3 the length of the adjacent side. Okay. Now with that, what we want to do is find the 6 trig functions. So let's start with the sine of angle A. And since I know what angle A is, I'll go ahead and replace the 30 degrees in there. I didn't do it for example number 10, but technically we could have also done it there. Okay, so sine of 30 degrees is going to be opposite over hypotenuse. Okay, so opposite side is 4, hypotenuse is 8. So 4 over 8 reduces to 1/2. Okay. Then we've got cosine of 30 degrees. Cosine is adjacent, which is 4 radical 3, over hypotenuse, which is 8. So that's going to be 4 radical 3 over 8. The 4 and the 8 can reduce down to 1 over 2. So we end up with a square root of 3 over 2. So these reduce. Oops. These reduce down, same as they reduce down here, up here. And then we have, sorry, not cotangent. Now we have tangent of 30. What is tangent of 30 going to be? Well, let's go back to definition. What is tangent in the definition, or what's the definition of tangent?
Opposite over adjacent.
Good, opposite over adjacent. So opposite side is 4, adjacent side is 4 radical 3. The 4s are going to cancel, and that'll give us a 1 over radical 3. But we have to rationalize because we don't like radicals in the denominator. So we get a square root of 3 over 3. Good. All right. So now for the remaining 3, we can just take these values and take reciprocals. So let me go ahead and highlight our final answers here. So take the reciprocal of sine and you get which function? Just let's talk about the function first. What is the reciprocal of sine?
8 over 4.
Good. So yeah. So in with our numbers, it would be our 8 over 4. We could also just take the 2 over 1 so that it's easier
Right.
for us. We don't have to reduce. Good. So that's a 2 over 1. And what would be the function for it?
Cosine.
Yeah, cosecant, right?
I mean cosecant. Yeah.
Yeah. Good. Awesome. All right. So our cosecant 30 degrees would be a 2. How about for cosine? What's the reciprocal function for cosine?
2 over square root of 3.
Good. So it'd be 2 over square root of 3. And what is the function?
Secant.
Secant. Excellent. Good. Now this one, we do have to rationalize, so we'll multiply top and bottom by a radical 3. And that's going to give us a 2 radical 3 over 3. Okay. That's the answer for secant. We have one more, cotangent. For cotangent of 30 degrees, what do we want to look at to help us find cotangent?
Tangent.
Tangent, good. So here's tangent. We got a final answer of radical 3 over 3. So we could take the reciprocal of this final answer, or we could take the reciprocal of what? Which would probably cut down the work that we have to do for this part. What was the original answer that we got for tangent?
1 over radical 3.
Yeah, originally we got 1 over radical 3. And then we multiply by this to rationalize it, right? But if we wouldn't have rationalized, that's what we would have gotten for tangent of 30. So if we work with that, it's actually more beneficial to us because we'll end up with a reciprocal, which is radical 3 over 1. And that just ends up being radical 3. Okay, so we cut down the rationalization part that we would have had to do if we would have taken 3 over radical 3. Okay. So those are our 6 trig functions. And just like, well, let me pause there. Do you guys have any questions here? And just like what we saw with the 45, 45, 90 in example number 10, we said it doesn't matter what the actual length, excuse me, of the side is. You still get sine of 45 is radical 2 over 2, or cosine 45 is also radical 2 over 2. The same is going to be true about a 30, 60, 90. And so if you take sine of 30 degrees, regardless of what these x's are, you're going to still get 1/2. Okay, I'll show it to you guys. Okay, so let's find sine of 30 degrees, which is opposite over hypotenuse. But now taking the opposite side to just be x. Okay, so if the opposite side is just x, then the hypotenuse is just 2x. And then the x's would cancel out, and we would get a 1/2. If we look at cosine, that one is adjacent over hypotenuse. So the adjacent side is x radical 3. The hypotenuse is 2x. And again, the x's would cancel out, and we would get a radical 3 over 2. And finally, we have tangent of 30 degrees, which is opposite over adjacent. And opposite side is x, adjacent side is x radical 3. The x's are going to cancel. And we're going to get a 1 over radical 3, which we would then rationalize to get radical 3 over 3. So those are identical to what we got for when x was 4. And what this shows us is the length, the actual length, doesn't matter. You're always going to get the same thing. Sine of 30 is a half, cosine of 30 is square root of 3 over 2, and tangent of 30 is radical 3 over 3. Okay. All right. Any questions there? All right. Now, so far, the trig functions, the definitions that we've seen, they only work for acute angles, right? It only works for angles that are between 0 and 90, not including the 90. So at this point, we might ask ourselves, well, what about everything else? Everything that's not acute? Well, in my case, we have to consider something called the reference angle. And so that's what this next definition is going to refer to. So a reference angle for angle theta, which is denoted as theta prime, is the acute angle that's made by the terminal side of the angle theta and the x-axis. The reference angle is defined to always have positive measure, and it doesn't need to be in standard position. Let me say that again. The angle has to be in standard position, but the reference angle theta prime does not need to be. Okay. So quite a bit of information. Let me just go ahead and break it down into its main parts, and we're going to use this diagram to show it. So the reference angle, first of all, is an acute angle. And so if you have a printout of these lecture notes, go ahead and underline acute, because that's important. I mean, it has to be between 0 and 90. And it's made by the terminal side of the angle theta. So if we take a look at this diagram, this is the terminal side. It's made by the terminal side of angle theta and the x-axis. Okay, so if I want to make an acute angle with this terminal side, I wouldn't make it with this one, right? Because then this is not acute. I would need to make it here. So it would need to be there. That would make this our reference angle called theta prime. Okay, and so that's why this is saying the reference angle is always defined to be positive measure, and theta has to be in standard position, meaning the initial side has to be on the positive x-axis, but for the angle theta prime, the reference angle, this does not need to be in standard position. Okay, so that's why this is possible. It's possible to have a leg, excuse me, it's possible to have this side that is not on the positive x-axis, okay, but it's only allowed for the reference angles. Okay, so any questions here? And give me just 1 second, guys. I dropped the cap to my handler. Just grab that real quick. Okay. So what we want to do now is try to come up with a formula for the reference angle for all of the angles or all of the possible quadrants that an angle can land on. So if you take a look at page 13, we have the 4 angles that terminate in one of the 4 different quadrants. This first one is an angle that terminates in quadrant number 1. So in quadrant number 1, the original angle theta, that one is between 0 and 90 degrees, right? So if it's between 0 and 90 degrees, and the way we know that is because up here, that's how we get 90 degrees, right? If it's like this, then we know it's 90. So if it's in quadrant number 1, it has to be between the 0 degree mark and the 90 degree mark. So in that case, if we try to form an acute angle between the terminal side and the x-axis, that's going to land us at this angle. And so in quadrant number 1, the reference angle, which is here, is going to be the same thing. Oh, sorry, I highlighted the wrong thing, but it doesn't matter too much. The reference angle is going to be the same as the original angle. Okay, so in quadrant 1, they're the same. In quadrant number 2, we have, and I guess I can use some different colors here. This is our angle theta. Okay. In quadrant number 2, the angle has to measure between 90 degrees, right? It has to be between 90 degrees and 180 degrees. Okay, between 90 and, well, I'll exclude the 90 and 180. And if we try to form an acute angle between the terminal side and the x-axis, we're going to end up with this reference angle here. All right. So remember, we're assuming that this is given. Okay, so suppose this is given. What we don't know is the reference angle. That's our goal. We want to know what that is. So to find that out, we can notice that when we add both of these angles together, what do we get? $180, good. So if I take theta plus theta prime, it'll give me 180. And since I already know theta, since it was given to me, I can solve for theta prime, the reference angle, to get the theta prime will be 180 degrees minus the original angle theta. And so that would be the formula that we would use to find the reference angle. Take 180 and subtract away the original angle, which will be somewhere between 90 and 180. All right. What if the angle terminates in quadrant number 3? Okay. Well, let's see. First of all, in quadrant 3, the original angle theta, which is again given, it's again given, so it has to be between 180 and 270 degrees, right? So it terminates somewhere in there, so that means that it has to measure somewhere between 180 and 270. And if we want to find the reference angle, again, we look between the terminal side and the x-axis. Now, we can't say it's this positive side of the x-axis, because if we do, then we form this obtuse angle, meaning it's larger than 90 degrees. So we're actually going to form it between the negative x-axis and the terminal side. And that'll give us the reference angle. And again, this is given. This is goal. And now we have to think about how we can relate the two in an equation. Okay. So let's see how we might be able to do this. This one's just a little bit trickier, but very similar to what we did over here in quadrant number 2. What if I were to say, okay, well, this here is 180, right? What do you guys notice about adding 180 to the reference angle theta prime? What happens when you add both of these angles? What angle does it give you? How about if I were to draw the 180 mark? I'll erase this for a second. This here also measures 180, right? That measures 180. So what happens if I take the 180 and I add it to theta prime? What does that give us? Well, that gives us the full angle theta, right? If I take 180 degrees and I add to it the reference angle, I get the full angle theta. Yeah, the regular theta, thank you. Right, so this is a regular theta. This is our theta prime. Okay. So take this 180 part, add to the theta prime, and you get the full theta angle. So now we can solve for the theta prime by subtracting a 180 from both sides, and we get theta prime is equal to theta minus 180 as a formula for finding the reference angle when the angle is in quadrant number 3. Okay. Do you guys have any questions for this part?
So theta prime is which one of the angles?
Theta prime would be this one here, which is this little angle here. It's our reference angle. It's this reference angle here. And we assume that we are given the angle theta and that we want to find out the reference angle from this given angle. So to do that, we use this formula here. Is that okay? Do you guys have any other questions? All right, let's find, we have one last one. What if the angle terminates in quadrant 4? Meaning, what if the original angle theta terminates in quadrant number 4? So if the original angle theta is in quadrant 4, here is the terminal side. And we want to draw an acute angle with the x-axis. So the only way that can happen is if we draw it with, sorry, I used the wrong color here. But if you draw it with the positive x-axis, and in that case, we're going to get the reference angle is this one here. Remember, we're assuming this is given, and we are trying to find the reference angle theta prime. So in quadrant 4, the given angle is between 270 and 360. And if we want to relate the two angles, what do you guys notice about adding together the given angle theta and the unknown theta prime or reference angle? What happens when you add these two together? Yeah, you get 360. Thank you, Christian. Yep, you get 360. So take theta at the reference angle, and we get 360 degrees, which means that we can solve for the reference angle to get 360 degrees minus theta. Any questions? So let's try an example with these formulas. Let me go to page 14. We have example 1. Find the reference angle of each angle. So for part A, we have 218 degrees. The first thing that I'm going to do is I'm going to draw the angle maybe on the side here, just so that we get a better idea of what we're working with. Okay. Excuse me. Okay, so vertex at the origin, remember for the original, this is like angle theta. For the original angle theta, it needs to be in standard form when we draw it. So we'll have the initial side on the positive x-axis, and then it needs to open counterclockwise in the positive direction. Up until the negative x-axis, that is going to be a 180 degrees, right? So how many more degrees would we need to rotate in order to make it to 218? Or, well, okay, maybe not the exact number. Let's not worry too much about the exact number. But which quadrant is this going to fall into? These are the quadrants. 1, 2, 3, and 4. Where is it? Sorry, go ahead.
Oh, quadrant 3?
Quadrant 3. Yep, exactly. Good. Because it's less than 270, right? And it's more than 180. It's going to be somewhere in quadrant number 3. And I didn't draw that too accurately, but for now we just want to worry about where, which quadrant it lands in. So it's going to be in quadrant 3, which means that the reference angle will be between the terminal side and the part of the x-axis that will make an acute angle. So the part of the x-axis that will make an acute angle is the negative one. Our reference angle is here. That's the reference angle that we're looking for, which we're going to call theta prime. This orange angle is the original one, but we just want this little piece, theta prime. So since it terminates in quadrant 3, the angle, the reference angle, is going to be theta prime equals what? Go back to page 13. For quadrant number 3.
Theta prime equals to prime minus, prime equals to theta minus 180.
Perfect, yeah. So our theta prime will be theta minus 180, good. So we'll take theta minus 180, okay? Or think about getting this whole angle theta and just removing the 180 part, and it'll leave you with this little part, theta prime. Okay, so that's going to be the given angle, 218, minus 180, and that is going to give us, good, yeah, it's going to give us 38. Excellent. That's the measure of that reference angle, 38 degrees. Questions there?
So it shouldn't. So I'm guessing it shouldn't be what is, it goes to what's closest to and what's not, and not what is next in the next quadrant, right?
Correct. Yeah. So it's a good question because you're thinking like not this part, right? Not this angle. Is that what you're asking about?
Yeah, I thought we were supposed to go to 270 as it was the next quadrant, but it turns out it has to be the one it's closest to, correct?
Yeah. So and basically the way to remember it is you should always have one of the sides on the x-axis. So if we would have drawn it here, right, I would have had the terminal side on the y-axis, not the x-axis. So we always want to have one of the sides on the x-axis, and that forces it to be this negative on the negative x-axis in order for it to be acute. Yeah. Okay, let's try this next one, 1387. Okay, I'm gonna draw the, because I think it's very small here, so, oh, I guess I have some room up here. 1387, let's try to draw that. So as you guys can see, this is a large number. It's more than 360 even. So we're likely gonna be completing maybe even more than one, more than 2 cycles. Okay, but again, here's my x, here's my y. 1387. Let's first find out how many complete cycles are in 1387 and what's the leftover. Okay, so 1387 degrees, let's see, if I divide by 360, oh, sorry, divided by 360, we get, okay, so we get 3, right? So we get 3. I'm just reading the whole number because the whole number tells me how many complete ones we get. And Lee Cox, thank you. We've got, you're mentioning there's 360, 720, and 1080 would be 3 full cycles. So that's the closest that we can get to 1380, right? Good. So we get 3 full cycles, and then to see how much is left over to still make it to 1380, we get 1380 minus 3 times 360 minus the 3 cycles, and we get 307 degrees. So 1387 is 3 full cycles plus 307 degrees. So if we were to draw that, we would have, that's 1 complete cycle, 2 complete cycles, and then 3 complete cycles. So that's this portion. Plus 307, where is that going to terminate? Which quadrant?
4.
Quadrant 4.
Quadrant 4, good. Quadrant 4. So somewhere there. Okay, because this is 270 and this is 360. Okay. And we want to make it to 307. So the 307 part is really just from this starting point up until there, up until the terminal side, which I'll go ahead and draw. Okay, so since I want to find the reference angle, and the reference angle has to be between the terminal side, which is here, and the x-axis that will make an acute angle, so that would be here, right? That would be the reference angle. I'm not going to worry too much about the 2 complete cycles. I'm just going to focus on this 307 portion, because ultimately I can just relate the 307 to the angle theta, oops, wrong color, to the angle theta prime. That should be yellow. And the fact that together they form 360, right? The other 3 complete cycles don't really have a contribution to that measurement. So what do I see here? I see that it terminates in quadrant number 4. And in quadrant number 4, I have that this angle theta prime plus this angle 307 degrees gives me 360. So we're actually treating this as theta. And then if we solve for the reference angle theta prime, we're going to get 360 degrees minus 307. And that's going to give us 53 degrees. Okay, so the reference angle is 53 degrees. Do you guys have questions there? All right, so what's the moral of part B? The moral of part B is that if you have an angle that has completed more than 1 cycle, then you always just want to find the coterminal angle with the least positive measure, meaning the smallest positive coterminal angle, like in this case that we found it to be 307, and then just work with that as your theta, okay, to help you find the reference angle. All right. So the last thing that I want to do today is I want to compare and contrast the reference angle versus a coterminal angle, because sometimes it's common for students to mix up those two because they are kind of similar. So I want to talk about the differences between those 2 types of angles. Okay, so reference angle is the one that we just talked about now. And one thing that is different is that it shares in common the terminal side with the original angle. Okay, so it shares the terminal side. with the original angle. I'll call it angle theta. And a coterminal angle actually shares which sides with the original angle? So everything that I'm writing here on the left-hand side, that's for reference angle. And everything that I'll write over on the right-hand side will be for coterminal. But a coterminal angle shares what sides? Well, it shares the terminal side, but it also shares the initial side with the original angle. So it shares the terminal side and the initial side. So that's one difference. Another difference is that a reference angle does not need to be in standard form. I mean, take a look at this example where we had the original angle landing in quadrant number 3. The reference angle was in quadrant number 3, and it didn't have an initial side in the positive x-axis, right? It had it on the negative x-axis. So with the reference angle, you don't need to have it in standard position. Okay, so it does not need to be. In standard position. Whereas the coterminal angle, any coterminal angle has to be in standard position. All right, here's another difference. A reference angle is defined to always have positive measure. It doesn't matter if it has, if it's in this negative, direction or anything. In fact, the reference angle doesn't really have a direction, unlike the original angle, right? The original angle here, because it's positive, we know that it opens counterclockwise. Same thing with this one. For a reference angle, it's always defined to be positive, so it doesn't really have a direction. Okay, so this one is always positive measure. But for a coterminal angle, it might have positive or negative measure. So those are some differences that you can, keep separated in your mind, so that when you hear coterminal angle, you don't confuse it with reference angle, and vice versa.